the same problem that green is not showing up. Okay. Okay, good morning, everybody. Today we will finish linear regression topic, and we will talk about feature selection for regression, how to understand if the feature is important for our prediction, for example, price prediction. Then we will talk about more metrics. Before we talked only about mean squared error and mean absolute error. We will talk about other metrics today. And if time allows, I will explain why L1 regularization actually forces some weights to be zero. Okay, so for the first part, I will just go through the notebook, and you can use that notebook as a reference for your homework 3 solution. Um, so let's open it. So I choose the data set with California housing that you worked on in your previous homework 2. And there were some missing values and nominal features, so I will just drop missing values and separate target and features. And also, I will create a random feature to understand if our method actually will detect a feature, irrelevant feature. So I create a feature that takes values 0 or 1 randomly. So let's see. I sample a random number, and if it's greater than 0.5, it will be true. If it's less, it will be false. And I cast them to integers. So it will be just a random feature. And it's interesting to see if our method will detect this absolutely random feature for this data. Then we split into train and test. And I split into train and test because we will use cross-validation today. So we don't need the validation set. But first we will convert nominal feature using one-hot encoder. And yeah, this is how our data set looks like with this random feature in the last column. So the first method to detect feature importance is to calculate some metric, some value. And this can be correlation, for example. We can calculate correlation between the feature column and target column and compare correlations and take the feature with the highest absolute value of correlation, for example. So let's plot the correlation matrix. And in the last, so as usual, I add the target column, and the last column shows the correlation between features and targets. And we can sort our features by this um, um, value by correlation. And if you look at the correlation with random feature that we created, this correlation is pretty high. It's higher than the real features. So, yeah, before we're going to choose these features by correlation, we want to calculate this correlation on validation set. But if you have just few data points, it's not reasonable to split this small number of points into three parts, into train, validation, and test, because this will actually reduce the number of points in your train part. So for this reason, typically we use so-called cross-validation. So in cross-validation, we split our data into, let's bring it up, cross validation. I don't see the image that I want to. So let's look at lecture notes. So in cross-validation, we have our data set, and as usually, we cut the testing part that we don't use until the end of validation of the entire model. And the remaining parts, we will split into k beans. So that's why it's called k-fold cross-validation. In this case, 4. And we will use the first, for example, parts as validation, and the remaining 3 parts as training. So we will train our model on these 3 and evaluate on this first part. Then we will do the same thing, but we will train our model on the first, third, and fourth parts and validate on the second. Then we will continue the same process. We will train our model on these parts, except the upper last, and calculate the accuracy or metric, which can be MSP, on the third part. And finally, we will train our model on the first 3 parts and validate on the last one. So for every process, we will get one number, one metric. So in the end, we can just average these metrics calculated on these validation sets. Just take the average, and this is called cross-validation metric. Now I will show how it works in code. So we can use the built-in cross k-fold split. And k-fold will return not the data, but it will return indices of the data. So, for example, in case of k equals 2, we have two splits. So the first split takes as validation set points with indices from 0 to this number, 8,000. Remaining points from 8,000 to 16,000 we will use for training. The second line splits this differently. We will use for training the first 16, wait a second. The first 8,000 points. And the remaining 8 points we will use as for validation. If we use number of splits, for example, 5, we will get 5 splits. Again, the first fifth will be used for validation in the first line. The second fifth, so you can see the indices are somewhere from our range. But these indices will be removed from these parts, and so on. So every time we use 4/5 of data as training and 1/5 as validation, but this fifth is taken from different parts of our data set. And in the end, so we train one model, we train the same model, but on the data and so on, we will get 5 scores, and we just take the average of these 5 scores. So why do we need, why it will work pretty well? You can think about the split when very similar data will fall in the first group. And then your metric may be very high for this split. But for another split, in the validation set, you will get the new data. And maybe for this chunk of data, the score will be very low. But in average, you will get the accurate estimation of the score of your model. If it makes sense, we can go forward. And so this is how we will actually evaluate our model without splitting into 3 parts, but we will use this cross-validation split on the training part. Okay, so I import some things here, and there is a built-in function select k best. So instead of writing a for loop and looking at the correlation for each feature, for example, so it will actually choose automatically k features with maximal correlation, for example. And here I'm using R. R stands for correlation. So scalar reach. Okay. So the first part, we will choose our features by correlation. Feature names out. Oh, wait a second. Yes, select best K. Um, so we want to see the best K. Um, aha. So the number of features that we had before, um, X train cross validation K shape was 13, but our model choose the first 9 features. Yes, so it calculated automatically the, wait a second, select best K. Sorry, let's double check. Um, I don't remember if it. Okay, so this function works a little bit differently. So it just tries k features and calculates the score, and it chooses the k features um, with the maximal score of the model. So it chooses, for example, first 9 features, trains the model only on these 9 features, calculates score. Then it chooses, for example, first 8 and 10th. So every time it chooses k features and calculates score, and then chooses the k features that actually resulted in the maximal score. And yep. I mean, you could do a little bit differently. So you could just, for example, look at the correlations and choose the features with highest absolute value of correlation, 9 features. Um, this best K works a little bit differently. It tries the set of K features and chooses K features with highest score. Okay. Um, we can use also, for example, we can choose features by this metric coefficient of determination. Okay. Then scikit-learn has function cross-validation score. Instead of creating these k indices manually, this function actually will split your data in these k folds and run your model k times and calculate the every score. So it will just provide the cross correlation automatically. And of course, um, we will use this built-in function instead of writing a um, writing a for loop over indices and calculate. Let's see. Yeah, you could run for loop and just use these indices for train and validation, and every time calculate score, and finally calculate the average score. So what is this, my XCV? Yes, so like I have here, for index in k-splits, so it will create X cross validation for each split k times. So instead of writing a for loop, we can use this built-in cross validation function. And in cross validation function, we can use the entire data set because it will split under the hood this data set into k faults and run this for loop for us. So let's run it. And here you can see, so the number of splits was 2. These are the scores for these 2 splits. And this is the score that our function returns, which is just the average of the scores for each split. Also, there is additional parameter shuffle. If you want, you can shuffle your data before splitting. If you use, for example, k-beans, then this function will run our model 3 times on different train and test validation subsets, and return the average score. And you can see that for some parts of our data set, score is lower, for some scores is higher, but we look at the average score. Okay. Okay, let's now choose by correlation. Here, I run a for loop, and I'm trying to choose, for example, one feature, 2 features, and so on, up to the maximal number of features. And by default, let's see. And the metric that I plot is R squared metric, but let's see, R regression, I believe it's correlation. Yep. It calculates Pearson correlation. Yes, so it's just standard correlation. Okay, so now we can look at this plot. The x-axis represents the number of features, and the y-axis represents the score. So what do you think, which number of features we can choose? If we don't want to take all 3, or all 13, sorry. Yes. Well, actually, 12 stands for 13 because I believe it flows from 0. I mean, if we don't want to take all features, maybe somewhere here, 9, about 9. Well, it's 10, but it's just crazy. So this is how we can choose the number of features by correlation. And then, let's see. Okay, we can also choose by mutual information. Remember, mutual information looks at non-linear dependencies as well. So so for mutual information, we use this parameter, mutual info regression. So it runs for every k from 1 to 13 this case best select, and also calculates the cross-validation score. So it takes a little bit of time. And the number of cross-validation bins is 10. Okay, so now if we look at this metric, the mutual information, that maybe we can choose smaller number. Well, actually, you can see that about 8, I believe, will be enough, because then we have just flat line. Or maybe we could choose even smaller number, maybe 7. And this function select k best has also parameter best features out. So we can look at the feature names. So for example, here I run my select best with k equals 9. And then I will I will print selected features. And let's see, I don't see the random feature here. But if I run with correlation, so now I just replaced mutual info by correlation, you can see that it chooses the random feature, which is which was just added arbitrary, so it doesn't make sense. But it just illustrates that correlation is not the best metric to represent the dependency between feature and target. And mutual information didn't choose this feature. Yeah, there is no this random feature between best 9. Okay, so now we decided which features to choose. We will talk about other methods. So this method is based on just these metrics like correlation or mutual information. So now we have chosen these 9 features, and we will fit our model only using these 9 features. So you can see here, I'm using only these features in my pandas data table and fit linear regression model. Oh no, in this case, ridge regression. Okay. And finally, I report the score of my model on the test path. So again, we choose features based on the training set, but we use cross-validation to estimate better the performance of our model. But we report the final score on the test part that we didn't touch at all during training. Okay, so if I report the accuracy, sorry, R squared on the entire data set, you can see that the score is a little bit lower than on the selected K. And it makes sense because we added random feature that just introduced noise in our data. Okay, so this was the first method, when we choose features by some coefficient like correlation, mutual information. The second method is based on the model. Last time we talked about lasso regression with L1 regularization. And you remember that it just set to zero some weights. So we will use this idea. For selection with model, you should use only lasso regularization, lasso regression. Okay, so now let's just run lasso regression on the entire data set. Let's see. And I'm not using even cross validation here. I just run on the entire training set. And here I print the weights for all the features. Let's see. Coefficients, yes, weights. So it doesn't include bias. And because I'm using pipeline, -1 stands for the element in my pipeline, and the regression was the last element, so that's why I'm using -1 here. And I sort values by absolute value, because the weights can be negative, of course, but we'll just look at the magnitude of these weights. And sort by the magnitude. And you can see that the feature with the lowest weight is actually this randomly graded feature. So it means that this method works. So in your homework, you can choose any method. You can use the previous one, you can use lasso. So it's just a few lines of code. And then you can say, okay, I want to choose 9 features. Then you just take the top 9 features with highest absolute value of weights, and you're done. So let's try to do this. So you can so column columns. What? Oh, array. What? Second. Oh, it's indices. It's index. Not index dot. Okay, so you can take the array with all features sorted by the in decreasing order of the absolute values of weights, and take, for example, the first the first 9, and and create this and feed this pipeline. Where is it? Um, and fit this pipeline on this selected features. Um, Mhm. And look at the score on the test. So it's 6496, and in previous case it was also 6496. So yep, so this is how it works. Okay, so this was the second method of feature selection based on the model. Oh, sorry, I I wanted correct markdown. So the next method is called recursive feature elimination. And I believe this is the most straightforward method. Um, so it works as follows. First, you take the first feature and train your model on this first feature and target. Then you take the second feature and train your model. Then you take the third feature. So you train your model with one feature at a time. Then you take first two features and train your model. Then you take the first and third, the first and fourth. So you take all the couples of features and train your model. Then you take all three features and also all combinations of three features and train your model. That's why it's called recursive feature elimination. And in the end, you choose the model with the features and the number of features um, with the lowest, with it depends what you want to maximize or minimize. If it's R squared with maximal value of your score, uh, which was evaluated by cross validation. So the problem with this method is that it's not time efficient. And for 10 features, it's fine, but maybe for 100, it won't work at all because it will be um, um, it will be um, if you want to so it will be the number. Wait a second, it will be 100 squared. Yeah, I believe it will be 100 squared time complexity because it will be kind of nested for loop. Okay, so let's run and in scikit-learn there is the built-in also function that will perform this um, uh, um, like two nested for loops that goes through the combinations of features and chooses the best case. Okay. It takes some time. Um, so I'm using this RFE, recursive feature elimination, first for one feature, then for the subset of two features, and so on. And then we plot the score for one feature, two features, and so on. And based on this plot, again, maybe the best number of features will be 9, because at this number of features we have kind of plateau. The score is not improving after that. Or maybe you could choose smaller number of features, 6. Well, looking at this plot, there is not much difference. And finally, okay, here I plot the features selected by lasso, but we did this. Oh, no, wait a second. No, I decided, okay. So I decided which number of features is the best. So then I again run my RFE on these 9 features. It will select 9 features. And finally, I will fit regression. Okay. Lasso I'm using as estimator, because as estimator you can use, for example, any model. It can be linear regression, it can be ridge regression. Here I'm using lasso. And if we plot print features out, again, you won't see the random feature in between these things. So it means that this method works. Well, and of course it works because we went through all the combinations. Okay, so this is all that you need for homework 3 to finish it. And you can use any of these 3 methods. You don't need to use all 3. Oh, no, it's not all. So maybe this function grid search will be also helpful. So do you know what is that grid search? So for example, you want to run your model with different parameters. And for example, so if you look at ElasticNet, so for example, you want to run the model like ridge regression and linear regression or lasso regression, ridge lasso. And for example, you want to try the number of features, k equals 1, k equals 2, k equals 3. So for example, you want to choose the model, but also the number of features. It means that you should try all the combinations of your model and the number of features. If you want to try, for example, some different parameters for example, in ridge regression, there is parameter alpha in front of the regularization term. Maybe you want to try some parameters alpha. Then you will need to add one more dimension and create a 3-dimensional vector tensor. And for example, here you will also choose alpha equals 0, no, 0.1, 0.5, and so on. So if we want to run our model on these different parameters, it's called the grid search because it's kind of creates a grid of these parameters. And there is a built-in function also in scikit-learn that where you just pass the dictionary which parameters you want to go through, and it will run and over all these combinations of all these parameters. So if you have 3 parameters, it will run 3 nested loops and so on. So let's look at this elastic net. So elastic net, as you remember, it's the linear regression with MSE loss plus coefficient times L2 regularization plus coefficient times L1 regularization. So the formula is here. So they have also, instead of 1 over n, sometimes people use 1/2 because it's a squared term, and when you take derivative, 1/2 and 2 will cancel out. So here they use 1 over 2n instead of 1 over n. Then they have 2 coefficients times L1 regularization and plus 1/2 times another 2 coefficients. Oh, well, they're the same, but different 1 minus L1 ratio times the L2 regularization. So why do I want to use this elastic net? Because if you use parameter alpha equals to 0, then you will get just normal linear regression. If you use parameter L1 equals to 0, then you will get a rich regression. If you use parameter L1 equals to 1, you will get lasso regression. So instead of using different models, I will use one model, but change these parameters. And based on these parameters, I actually will get different models or rich regression or lasso regression. So it's more convenient for grid search. Does it make sense? Okay. So here I create my pipeline, select best case, standard scalar, and elastic net. And in pipeline has parameters. You can print them out using get params. So it returns the dictionary with parameters. And these are parameters that you can actually change in your grid search. So, yeah, for example, here is L1 ratio. By default, it's 0.5. Alpha and other parameters. K, best K for now, it's 10 by default. So we can import this grid search from scikit-learn, grid search, which will provide this selection based on cross-validation, CV, and create the list of parameters. In my case, I create, I want to try different metrics. So I'm using mutual information and regression. I believe it's a spin. I don't remember. Let's double check. What is that F? R was the normal correlation and F regression. Aha. So it works as normal regression for continuous features, and it works as F-score. We will talk about this when we will talk about classification, which is next week, for no, nominal features. Okay. Then I want to, so it's just, in our case, it's just normal regression, relation. Then I want to try, for example, 9 and 8 features. Then I want to try different parameters of alpha and then different parameters of this L1 ratio. If it's 0, then we will get rich regression. If it's 1, we will get a lasso regression. And if it's 0.5, we will get elastic net, the combination. So I will, with the last line, I will try 3 models. Different models. And in your homework, I don't recommend to use like many parameters because then it will run forever. It just will go through all these parameters. So I initialize grid search with this dictionary of parameters. Cross validation beans is 5 and fit. Sometimes it doesn't converge. So that's why we have this convergence warning that maybe you need to increase the number of iterations. It's fine. Yeah, it says that coordinate descent didn't converge. Okay. Yeah, you can see that only with um, three three different arrays of parameters, it takes a while to go through all these parameters. But in the end, it will actually return the parameters that resulted in the best score. And then we will use these parameters to train our final model and deliver the score on the test part of our data. Okay, so you can see that best k resulted in k equals 9. Well, standard scale is not interested. And with criterion mutual information. And the best model was elastic net with L ratio 1, which is lasso. And 0.5. So we can look at the feature names that were selected by this grid search. And again, we don't see here this random feature. Great. So finally, we can train our model using mutual information and this list of best features. For some reason, I'm using this GD regressor, but you could just use ElasticNet. It's the same. And then we predict values on the test. And finally, we can calculate the score on the test. Let's see. Pipe score. Well, it's pretty the same that we had with our first method, the value of R squared. And the remaining code I have here just shows how to get the prediction of the price for new data point. So let's take, for example, the first point from our data set with, so it has parameters, these features. And I want to predict the price for this apartment with these features. So let's see, but it's normalized because that's, or no, wait a second, what's the total bedrooms? Right, it's two, okay. I'm not sure why the total number of rooms. Okay, maybe it's multi-apartment building. I don't know. So we can take only features that we selected with our previous model method. So we'll just use the selected features. And then we won't have this random feature that we had here. And finally, we can apply our model predict, but because it expects data frame, I'm using here double brackets to get two-dimensional array. And voila, this is the predicted price of the apartment. Well, it was many years ago, so maybe at that time this price was reasonable. Now you can find for this price, I believe, even in Rochester. Okay, not needless to say about, about California. So, okay, yeah, and this is how actually it's calculated. It's just a linear function. You can take coefficients, the coefficients and intercept, and then just use the sum intercept plus the coefficients. Where is it? Yeah, I'm doing it here. I'm taking the first feature names and take the dot product with coefficients and also add the intercept. And I get the prediction, which is, let's see. Oh, wait a second. Oh, the first, I'm a little bit confused. The first one, oh, okay. Sorry, this is the true value, 245,000, and this is the prediction, 200,000. So when I calculated the linear function, I actually have the prediction, 200,000. Okay, so that's it about linear regression. Now let's talk about different loss functions and why lasso regularization works. Do you have any questions about this previous part? Yeah, the last one was kind of review of the linear regression. Um, Okay. Different metrics or loss functions. You remember last time we introduced an outlier, and we applied ridge regression and lasso regression, and they resulted in different um, regression lines. One tried to fit outliers, another worked pretty good. So the function that we know, the first one, mean squared error. So it's the quadratic function. It's a nice function because it has unique minimum, and it's easy to optimize, take the derivative, square root. The next function was mean absolute error, which so this line is error, and this line is the function on the square root of this error. And you remember that mean absolute error function penalized less large errors than the squared function. But it penalizes equally like over prediction if you predicted the apartment price like higher than its actual price, and equally the under prediction if you predicted the price lower. And maybe you don't want to estimate, if you want to sell your apartment, you don't want to or to underestimate your apartment and sell it like twice cheaper than its price. So if you sell it, if you will advertise it with high price, it's fine. Nobody will buy it, but also you won't lose money. So to take care of this, we can use asymmetric function, which is which is wait a second. Okay, it will be later. Asymmetric function. Which is called quantile regression. 1 second. Okay, here is this asymmetric function. So it will penalize, for example, less the over prediction, but it will penalize higher the underestimation. And here's the formula. If our error is positive, so it means, for example, we over predicted, then the slope will be tau, and if it's negative, the slope will be wait a second, tau minus 1. Yes, and tau, if tau is between 0, 1, then tau minus 1 will be negative. So we will get negative slope. But if you think about, like, if you take tau 0.1, then the negative slope will be 0.9 negative. So this is called the quantile regression. And if tau is 0.5, then it's exactly the same as MAE. And that's, you remember last time I used quantile regression with parameter 0.5 just to implement MAE loss. Okay, so next loss function that you can use also is a combination of rigid and lasso, of MSE and MAE. And it's called Huber. So Huber loss function performs exactly the same as mean squared error for small values. So it will be parabola for small values. Between um, so there's factor 1/2. So if z equals epsilon, then it will be a negative epsilon over 2. Epsilon squared, actually. Epsilon squared. And epsilon over 2. So it will perform as parabola for small errors, but for large errors, it will continue. It will be continued as uh, absolute value function. So it's kind of if you continue these lines will represent the absolute value function. So it will be differentiable, but it won't penalize large errors as MSE does. So it will be stable for outliers. It's called Huber function. Then there is another loss function, mean average percentage error. So, and you can see the formula, it has the error in the numerator and the true value in denominator. So typically this metric is used for stock for the supermarket stocks, because if you think about the error in units, like your prediction was incorrect, for example, in by one package, and you divide by the true number of packages, then you will get let's see. If you multiply also by 100, you will get 1% error. If your error is 2 and you divide, you will get kind of 2% error, and it will represent your error in number of items. So this is the idea of mean average percentage error. Now, also it's used in time series predictions because typically we want to predict some sales, and they are typically in units. Well, we know you're familiar with R squared, so I won't repeat R squared metric. And there is also mean squared log error. So it's the difference, but the difference not between prediction and targets, but between logarithms of prediction and targets. And we add 1 to avoid logarithm of 0. So this metric is used if you want to get just rough estimation up to the order, like up to tens, hundreds, and so on. Okay. And it looks... Okay, we have 4 minutes. I will explain then why lasso regression works. And maybe next time to completely finish the linear regression, I will also provide one example when we scale target. Before we scaled only features, but sometimes you also want to scale the target. But we don't have time for this today. And typically we actually apply logarithm to the target, and it results in better scores. Okay, so now let's talk about why lasso regression works. There is a lot of interesting material that I would like to cover. Okay, but we should also move to the next topic, the linear regression for classification tasks. Okay, move these drawings. So, oh my gosh. So, you remember that the if we want to visualize loss function and we take the projection for L1 for Manhattan distance, it will be a square, and for Euclidean distance, it will be a circle. And the loss function in our case is just the sum of, for example, MSE loss and regularization term. So MSE loss I visualized by this ellipses, and it's a projection of our paraboloid. And the second term I visualized with this square. So if you look at if you look at, for example, the orange line, the orange level curve actually intersects my circle in 2 points. It means that if I take my weights in this intersection, and in this intersection, the weight W1 should be 0. W2 should be non-zero. It will be exactly the same as I take weights at this point, and then both weights will be non-zero. So for ridge regression, it doesn't make difference to force one weight to be 0, because there is another point with exactly the same loss function value. But for lasso regression, of course, I just provided some example of loss function. If our loss function just has this position, then it touches our square at one point. That's why it will force the other weight to be 0. Of course, the loss function, this ellipsoid, can be positioned differently, and also with lasso regression we can get non-zero weights. But this provides some idea why it works. And if you want to get more details, then I actually provided a link to the video how to calculate this lasso regression. Okay, yeah, that's it for today. Still asleep.
So for the
Yes.
first loop, we're expecting that it'll like break and get a